Hello and welcome to the Spatial Structures Movers and Shakers interview series as we look ahead to the ISS Annual Symposium and Spatial Structures Conference, organised by the University of Surrey and taking place virtually in August 2021. My name is Mark Richardson and today I'm joined by Matthys Levy, who is an author and an engineer. Matthys has been designing domes, buildings and bridges for more than 50 years. His projects include the Baghdad Stadium, the Rose Center for Earth and Space, and the Plata Stadium in Argentina. Matthys is the author of several books, including the best-selling classic Why Buildings Fall Down with Mario Salvadori. He is also a Chairman Emeritus at Weidlinger Associates, a structural and civil engineering firm. Matthys, thanks very much for taking the time to join us today.
Well, thank you. My pleasure.
Matthys, it's a real pleasure to have you on the Movers and Shakers interview series. We start by asking our guests about the period of lockdown. How has that been for you in the United States?
Actually, it has not been that terrible. I mean, we've had rather good experiences. We've all been vaccinated quite a long time back. And so we've been able to move around more freely in the last couple of months.
That's good to hear that things are slowly improving and getting better. We also ask our guests about their career journeys, which perhaps we could come on to in a second. I was interested, you are obviously a novelist, and it's unusual to have a writer of fiction on our Movers and Shakers interview series. So I wondered if you could briefly tell us about your fiction writing.
Well, about 5 years ago, I decided to write a book, a novel about construction because I knew a lot about it. And I simply had to be able to talk about the people involved in construction, the architects, the engineers, and so on, contractors. And I put that together called Building Eden. It's about a building of a high-rise building in the time of 9/11. And since then, I've started a new novel that is more of a dystopian novel, talking about the consequences of global warming, or climate change as we now call it. And again, it involves a number of people who had to deal with what the consequences were of climate change.
It's great to hear. It's great to hear you applying your engineering and science skills in a slightly different avenue. So thanks for sharing that. And as you alluded to, it's based on your experience in engineering and wider fields. And with that in mind, maybe you could give us an overview of your career journey to date.
Yes, actually my career started 70 years ago, 1951 when I graduated from college. But then there was a 5-year interval where I did work for a bit of time. Then I was drafted in the Army, had to go to Korea for several years. And then I came back and went to graduate school. And that's where I met Mario Salvadori, who became my mentor, my friend, and my partner. And we ended up writing books together, a number of books together, actually, including Structural Design and Architecture, which was the first one in 1967. And then afterwards, we continued with all the Why series, Why Buildings Fall Down, Why the Earthquakes, and so on.
Amazing, yeah. Thank you very much for sharing that. And we also, we're always interested to know about projects you've been working on, currently or very recently. So perhaps you could give us some examples or an example of a project you've been on recently.
Well, the most recent project actually is the one I was going to talk about in a few minutes. And that is a canopy in New Orleans at the World War II Museum. It's a large canopy. It's about 148 meters by 41 meters, triangular in shape. And it covers a space in the center of the museum complex, which they call the whole thing the canopy of peace. And the area between the different pavilions, they call the parade ground. Very militaristic.
Superb. Well, I look forward to hearing more about that. And I suppose to that point, we'll now move to the middle section of our interview, which is entitled Your Space, Your Structure. So at this point, I hand over the presentation rights to Matthys, who will be sharing a presentation for 15 minutes or so on a topic relating to spatial structures. So without further ado, over to you, Matthys.
Okay, so in the time since 1956, when I really started working with the Weidlinger Associates, and specifically with Mario Salvadori, I began by doing shell structures because I had learned shell design from Mario, and the firm really wanted me to be the specialist in shell structures. So the kind of projects we started with were relatively simple projects. We started with wooden shells. There's a series of small wooden shells that we built for the George Nakashima compound. George Nakashima is a woodworker, so he wanted to build things in wood. And these are plywood, essentially plywood shells. There's a conoid. We also did a hyperbolic paraboloid. And then we continued with different combinations of conoids, hyperbolic paraboloids. And these were all done with, say, 3 layers of plywood, thin plywood, that were just simply nailed together. And as you can see, these are not large buildings. They're maybe 10 meters in across. I became involved in one of the first concrete structures that was being considered at that time. This was a concrete version of the hyperbolic paraboloid. This happens to be in Jamaica, and it was based on a model of a house that Catalano built for himself in the U.S. But it's the same kind of an idea, except it's quite a striking. It's interesting. It's called the Strike House because Strike was the owner, but it's a striking presentation of what a hyperbolic paraboloid can be. We then moved along and we had the contract to design the St. Louis Priory. Now, St. Louis Priory, you can see, is a combination of 3 layers of arched structures. And the idea there was these were conoids. Each one of them was conoid, and they're all different types of conoids. The thing we in those days, of course, we didn't use computers that much because they simply were not very powerful. So we had to learn one of the most important things, which is how to approximate a structure. What can we do to model a structure mathematically in such a way that we can actually analyze it and design it? So for instance, the folded plates, we analyzed as beams, scalloped shells, we analyzed as arches, space frame as a plate, membrane as cables. So this is how we ended up doing our analysis. This was the first and perhaps the most important structure we worked on. And it's about 40 meters high, and total of 40 meters high. It's also about a 40-meter diameter structure. Each of these elements was replicated by a single form. We then moved on and worked on this much more of a free-form structure. Again, we were able to design it through approximations. Between the columns, we approximated arches. We modeled it as arches between the columns. And then the center portion is a dome shell. So that's how we were able to do the analysis and actually get it built. Unfortunately, this is a model of the mosque we designed in Baghdad. We had contracts to design many buildings for the Baghdad University, but unfortunately, this building was built at the end of the series, and we were no longer able to get a camera in there to take a picture of the actual structure itself. But again, I could point out that the upper portion was designed as a shell, as a dome shell, and then between the base points, we essentially designed it as an arch beam, and we were able to model it that way and actually get it built. Interestingly enough, before it was finally constructed, we had then the ability to analyze it with a computer, and we did so, and with breaking the whole shell structure into sections and then analyzing the whole thing. We were very close to the original analysis. There was some savings in material, but not significantly. Next, we move on to another kind of freeform trail. This is a called La Concha in Puerto Rico. It's a nightclub. It started off as a nightclub for a hotel. And again, it's a structure that could be analyzed as arches, curved element arches, and it was done so. And we did this back in the late 50s, early 60s. Then I moved into, there's a quiet period where I designed many high-rise buildings, and then I moved into this, which was really quite a change for us, and that is the Georgia Dome. This is a tensegrity roof structure. What I mean by that is it's a roof structure that is built up of cables and flying posts, one after another, until you get to the crown of the roof, and the whole thing is topped with a fabric roof. And this is a kind of a huge structure. It's about size of obviously a football field, even in a British football field, and it was very light, extremely light, for the spans that we were dealing with. Unfortunately, it was torn down a few years ago because the town decided that they wanted to have a new stadium, not necessarily bigger, but with more boxes in it. So this unfortunately died. But it served as the model for us for another building that is very similar, but somewhat different, and that is the roof structure for a stadium in Argentina called La Plata. And La Plata is, again, it's a similar type of structure, and you can see it here more clearly because if you follow the cable lines, you can see where the posts are and where the cables go toward the peaks. What's unusual about this form is that it is a two-peaked roof. There are actually two peaks. The reason being that the town of La Plata has two football teams, soccer teams, and each one wanted to have an identity. So therefore, we ended up with this unusual shape. But as you saw before, it is now built to this extent, and the center portion is going to be filled in within a year. Now, beyond that, we designed other similar type of structures. This one, for instance, is in Japan, Saitama. This was not built, unfortunately, although it was, again, a very economical structure, but they decided to build something else instead. The next this kind of gives you an idea of the arrangement that was made for this particular. You have a ring beam, and you have posts that go to, and posts and cable to go to the actual fabric structure itself. The next phase really was the design of the Javits Convention Center in New York. Now, this is a huge convention center built in 1985. It's about 24,000 square meters. It's supported by columns and about 28 meters on center, and it has almost as much glass and space frame on the faces as it does in plan. It has about 22,000 square meters of space frame and facade. Now this was extremely successful. It still is there. It's not going to be torn down anytime soon. In fact, we had the opportunity in 2018 of renovating the structure. There were some problems with the roof, and we changed it to a green roof The structure itself was not changed in any way. So the basic structure is all this pentagonal space frame, and it goes both vertically and horizontally. You can see in this is the main entrance, and you can see how it climbs up toward higher and higher sections. And finally, you can see here how the whole structure steps down and sits on the columns below. Now, the similar type of thing, but quite different, is the World Bank. The World Bank in Washington has a center atrium surrounded by office buildings. In the center atrium, there is a space frame roof that is picked up by these columns, that are tree columns that come to points on the space frame and actually transfers the space frame loads down to a concrete shaft. These diagonals you see going down to the shaft are obviously steel. And then I'll finish up with the current building that I'm working on, which is the World War II Museum in Atlanta. Atlanta wanted to host the World War II Museum. They had already started with a single building, actually across the street from this complex. You can see it on the right. It's called the Louisiana Pavilion. But they built these other pavilions, and they left the center section open as a, excuse me, as a parade ground. But they wanted to have the parade ground covered in some way, not fully covered, but at least covered to provide shade. As you know, New Orleans is pretty far south. It's a very hot area, and the shade would be very desirable. And this is an image of the actual piece itself under construction. It's still not complete. It's a triangular roof, 148 meters by 41 meters, supported on these 4 columns. And it is all in, actually space frame sections that are linked together. And it is meant to then have, let's see if I can do this now, just a second. You can see this is the eventual way it will look when it's completed. And what you see in the roof itself are fabric panels which are inserted into the roof and which provide the shade that was necessary. These fabric panels, and you might be aware that New Orleans is in an area that has superstorms. So these were designed as sacrificial panels. They could actually fail without causing any failure to the structure itself. And that, I think, pretty much summarizes what I have to say. This is the final view that I have, and that is the end. Thank you.
Matthys, thanks so much for taking us through your presentation there. A really wonderful range of examples of structures over quite an impressive breadth of time, some wonderful shells and domes amongst others. I've really enjoyed it. So thank you very much for taking the time to share those with us. We're now going to move to the final section of our interview, which looks to the future of spatial structures and in particular the 2021 conference. Now the conference, as you may know, Matthys, has the theme or motto of inspiring the next generation. So what advice would you offer to aspiring engineers or architects looking to enter the field of spatial structures?
Well, I think the most important thing that there are many opportunities, clearly many opportunities, because large roofs, even smaller roofs, can easily be built using some kind of spatial structure, either a fabric and steel spatial structure or even concrete structures. There are examples of those as well. So I think the main thing is that one has to be open to new ideas and be able to attack them, because the analysis itself is not that difficult once you have supercomputers available as we have today.
Great advice there. And sort of building on that, what do you think are the most pressing challenges in the field of spatial structures? with respect to some of the current global challenges?
One of the main things I think that, and this is really the topic of the novel that I have under consideration, which is the fact that we are entering a new era. And this new era will be an era of climate change, rapid and unexpected climate change. We're already feeling some of the effects now as the areas in the lower southern areas of this country and of Europe and the northern areas of South America are all heating up and becoming, in many cases, no longer habitable. So we have in the United States now this problem of people who live in say Central America who want to emigrate to North America because they can no longer live there comfortably. Now this is going to go on forever. Now we have to come up with ideas to not only accommodate them, but to find housing for them, to find maybe new forms of housing for them, just as we found new forms of housing for people who after the Second World War.
Yeah, some very important ideas there, Matthys. Thanks for sharing those, and look forward to reading that novel when it's ready. That sounds like it covers some very poignant and powerful themes. So so look forward to that as well. Well, Matthys, we've reached the end of our interview today. Thank you very much for your time and presentation. Just some notes for those watching our Movers and Shakers interview series. Registration for the 2021 conference is still open. We've now had over 350 people from more than 40 different countries register. Please do head to the conference website for full details and information regarding registration. If you've enjoyed this video or indeed any in the Movers and Shakers interview series, please remember to like, share and comment. All of your views and thoughts are welcome. And thanks to all those who have engaged with the series to date. Our social media has now reached or even surpassed 57,000 total views, and our YouTube page has passed 500 subscribers, which is wonderful. But for now, Matthys, thank you so much for talking us today. Really enjoyed hearing about your work and career. And as we move ever closer to the 2021 conference, hopefully we'll get the opportunity to catch up with you again. But for now, thank you very much.
Thank you, and look forward to the new book called Aftermath.
We're also looking forward to that, Matthys. Thanks very much again, and speak to you soon.
Thank you.